Well, the first thing I'm going to say is that D can't possibly be right. If you just look at the units, a capacitance divided by a resistance is not a current, and so that's right out. A, B, and C all turn out to be wrong as well. I'm not going to go in detail through why. I'll just say write some loop laws, and the loop laws will show you that A, B, and C can't be right. So that only leaves us with E. Well, why is that current 0? How do we know? Well, I've told you that the charge on the capacitor is 0 before we close the switch. Well, just after we close the switch, the charge has to be the same as what it was just before. And so the charge on that capacitor is 0 right now. And the potential difference across the capacitor is proportional to the charge, so it's 0 as well. And that capacitor is in parallel with that resistor after we close the switch. And so there is a 0 potential difference across resistor 2. And a resistor with no potential difference across it will have no current through it. So now let's apply the same sort of reasoning to inductors, and we'll start by looking at what happens just after moving a switch. So here we have the switch, which has been in position A for some time. And for this circuit, that means there will be a current which flows through the inductor and around the loop that it's in. And now let's move the switch to B and think about what happens. And in particular, we'll focus on just after moving the switch to B. Well, remember what an inductor does. An inductor resists changes to the current through it. And so, in other words, it must take time for the current through the inductor to change. But just after we've moved the switch, there hasn't been any elapsed time for the current to change. And so the current has to be the same through the inductor just after we move the switch as it was just before. And again, all of those same arguments will apply to the situation of moving the switch back from position B to position A. Now let's think about a long time after we move the switch. So let's say we've moved the switch to B some time ago. Well, again, let's look at a loop law. Any time after we've moved the switch to B, this is the loop law for this loop that I've indicated. And note that since we know the direction of the current through the resistor, we know which side of the resistor is the high potential side, and this loop law tells us since we're going through a potential drop as we walk through that resistor, we must go through a potential rise as we walk through the inductor. So that says that this term, which is describing the potential difference across the inductor, must be positive, despite that negative sign out in front of it. Well, the only way that's possible is if di by dt is negative. In other words, the current must be decreasing, and that makes perfect sense. So we know that the current is decreasing, and eventually, that means the current will be 0, at which point as well, since if the current is 0, IR is 0, that means this potential difference will also be 0, and so the current stops changing when it reaches 0. Now let's think about moving the switch back to position A. And again, we can think about a loop. This time we want to think about this loop. So any time after moving the switch, the loop law looks like this. And the current we would expect now to be increasing, and so the potential difference across the resistor must be increasing, and so the potential difference across the inductor must be decreasing. Well, that tells us that di by dt is decreasing. Eventually, di by dt will be 0. Or in other words, eventually the current is constant. Note, the current isn't 0 now, it will simply be some constant value. And this is the endpoint for after we've changed a switch when there's an inductor. Eventually the current will be constant through all the inductors in the circuit. So again, let me summarize the situation for inductors. Just after we've moved a switch, the current through an inductor must be whatever it was just before we moved the switch. And a long time after the switch is moved, the current has stopped changing in any branch containing the inductor. In other words, any branch containing an inductor will have a constant current in it a long time after the switch is moved. And note that since the EMF across an inductor is proportional to the rate of change of current, that tells you the EMF across an inductor is 0 a long time after a switch is moved. And again, there's a caveat. This isn't generally true if there is a capacitor in the same branch with the inductor. And again, what we mean by a long time is long compared with a time constant, which we've seen how to get, except that it would again be to do with an equivalent inductance and an equivalent resistance of the whole circuit. Let's work another example, and I'm going to go through this one fairly quickly because what you're seeing is that it all just comes down to writing loop laws and junction laws with a few additional things to consider. So let's think first about all the currents before we close the switch, when the switch has been open for a long time. I'm going to note that I've already indicated the currents on here and given them names, and I3 is the same as what you might call IL, the current through the inductor. And so we know that initially I3 has been constant for a long time, and so the EMF in the inductor is 0. And I'm now going to indicate some junctions and loops and write the laws for them. So this loop law and this junction law will always be true, but now let's think of this specific case before we close the switch. So first of all, IC is certainly 0 when that switch is open, and so our junction law for junction alpha reduces to just that I3 is equal to I1. And so I'm just going to call that I, and then that makes the loop law for A much easier because I also know that initially before I've closed the switch, di3 by dt is 0. In other words, there's 0 EMF from the inductor. And so that loop law just becomes, which I can solve for that current. And if you run the numbers on that, you're going to find that it comes out to, and that is both I1 and I3. Now if I wanted to find the rest, and I'm going to skip over it, I could do this loop law to easily get I2, and then I could perhaps do this junction law, and since I already know I1 and I2 at that point, I could get IB. So now let's find everything just after closing the switch. And a useful loop to think about will now be this one, which I will call B. And in particular, what I know just after closing the switch is that I3, which is the current through this inductor, will not have changed. And so that allows me here to see, if I wish, what the rate of change of I3 is, because if you just work through that current and that resistor, you find that this potential difference is 1 volt, and we know that that's 2 volts, and so we know the potential difference across the inductor is 1 volt, and that it is a drop going this way. And so in other words, the inductor is working to push against the current through it. It's fighting the current increasing. So now a useful loop law to do, and I'm getting a few too many loops on this diagram, so it's getting a little messy, but if I do this loop, that is a loop that contains only one resistor, and so that would let me solve for I1 very easily, and then I can use this junction law to find IC. So let me just do that. And I can now use the junction law for alpha to find IC, because I now know I3 and I know I1. If you do that, you'll find that IC is apparently negative 0.013 amps, and so it is in fact in the opposite direction to the one I indicated here. Finally, let's do a long time after closing the switch. And so now the current through the inductor, which is I3, is constant. And so di3 by dt is 0, or in other words, the EMF in the inductor is 0. And that means I can use loop B very easily to solve for the new I3. I can again use this loop to show that I1 is exactly what it was before, which means I can again use this junction to find IC, and this time I find that it is negative 0.053 amps, and so it is again going in the opposite direction to the one indicated, and I could now work through a bunch of other junctions and this loop and so on to find the rest of the currents.